What I want to go over with you are the differences between acids and bases as we talk about them in organic chemistry versus nucleophiles and electrophiles. So from general chemistry, there were several definitions of acids and bases. We are going to look at the definitions that we use in organic chemistry. So in organic chemistry, what we define an acid as, they are proton donors. So we're literally looking for something that's donating an H+. And a base in organic chemistry will be a proton acceptor. So they're going to gain that proton. So that's what we're literally looking for as we try to talk about an acid and a base. Now, in general chemistry, we referred to a Lewis acid as an electron pair acceptor. In organic chemistry, we call that an electrophile. And a nucleophile is also known as a Lewis base, which was the electron pair donor. So these are important definitions for our purposes, and we are going to use them significantly in this talk that we're about to go through. And it's really important that you have an idea as to what these two differences are, so I thought an example would be very illustrative. So the example I'm going to show is an example that you get in chapters 4 and 5 between two reactions that are very similar and yet are very different. And these are your substitution reactions versus your elimination reactions. And I find many students have a very difficult time knowing when you should do a substitution versus an elimination. And it really does come down to whether something is acting as an acid or a base, or an electrophile and a nucleophile. So I'm going to give you some examples that I think will be very illustrative. So in both of these chapters, you're able to take alcohols to either alkyl halides or take an alcohol to an alkene. And it really does depend on what the acid is doing in both cases. Is the acid going to help us set up a situation where we're going to do acid-base chemistry? Or is the acid that we are adding going to help set us up for a situation where we need to do electrophile nucleophile chemistry? So I've got an example for us that I hope will help with this situation. We are going to use 2-methyl-2-propanol. There are others that we could use. Now, I'm using this one specifically because I want to demonstrate the difference between doing an SN1 versus an E1, because it can actually do both. You also kind of need to know when you should be doing SN2 versus E2, and I will also show something along those lines as well. But this alcohol can be treated with two different acids, and depending on which acid you use, different things are actually going to occur. So the first reaction that you were introduced to in chapter 4 was using a hydrogen halide as your acid source. Now, the reason that we do in the first step acid-base chemistry is due to pKa's. You have to be able to identify which of these chemical species is the better acid, and as a default, which one is going to be the base. So I'm going to go to your Pka chart, and what we're going to do is really compare the most acidic protons on the alcohol and for HBr to kind of get an idea as to what the relative pKa's of these different protons are so that we can identify the acid and the base. Now I realize a lot of you already know which one that is. It's going to be HBr, but we want to look at why it's HBr. So this is a Pka chart. And up here at the top, you can find HBr right here. And HBr has a pKa of negative 5.8. That's important. That tells us that this is a strong acid. And if we try to find a comparable pKa for an alcohol, they are in the same realm as water. And you can see that methanol, right here, water, ethanol, isopropyl alcohol, tert-butyl alcohol. These are our examples of alcohols on this chart. And all of these alcohols have pKa somewhere in the range of about 15 to 18 pKa. And so they're much weaker acids. And if you were to look at the protons on the methyl groups, you can notice that the pKa's for a proton and an sp3 hybridized carbon is about 62. So those are not acidic protons, and they are not the ones that we're going to be considering. So the most acidic proton comes from HBr. And again, that pKa that we looked up a moment ago was negative 5.8 for this proton. So we are going to transfer it. And to do that, we have to have a proton acceptor on the other molecule. Our proton acceptor will always have a lone pair, and that's going to be our oxygen. So our oxygen is going to use its lone pair to pick up this proton, and we're going to break the HBr bond. Bromine is more electronegative, so bromine will take the electrons with it. And as we do this, we produce an alkyl oxonium ion, and bromide anion. So the goal right now is to see if this was favorable acid-base chemistry, because if you're doing acid-base chemistry, the entire goal is to form a weaker acid-base pair. If it doesn't form a weaker acid-base pair, you shouldn't be doing it. And so you need to identify what the conjugate acid and the conjugate base are on the product side. So on the reactant side, our alcohol acted as our base, HBr acted as the acid. So the conjugate acid on the product side is this alkyl oxonium ion. That's where the proton went. And the conjugate base here is bromide. So now what we're going to do is we're going to look up a relative pKa for an alkyl oxonium ion to know if this was favorable acid-base chemistry. So you go back to the Pka chart. And we're going to go to the other of the two. And as you can see up here at the very top, there's something called Ethel Oxonium Ion right up here. And that has a pKa of negative 2.4, and hydronium ion has a pKa of negative 1.7. Both of these are protonated oxygen atoms. So they're still strong acids. But as you can see from the placement on the chart, they are weaker acids than HBr. And so this is going to be favorable acid-base chemistry. I don't know precisely what this acid's pKa is, but I know it should be around negative 2. So favorable acid-base chemistry is occurring. Now, before I keep going with this example, I want to show you another one that you see in Chapter 5, which is very similar chemistry, but with a different acid. So we're going to use the same alcohol. This time, though, instead of using a hydrogen halide as the acid, you use an oxyacid. And the one that is typically used is sulfuric acid. So again, we're going to identify the acid and the base. Now, I know that you know from general chemistry that the answer should be sulfuric acid. But I want to make sure you see it again with this Pka chart. So if you go up near the top again, you're going to find sulfuric acid. And sulfuric acid has a pKa of negative 4.8. So it's a very strong acid. That's going to be the acid in our example. And again, the goal is to always make a weaker acid-base pair. It does exactly the same chemistry because we have a really good proton donor. Sorry, my arrow is disappearing. And an acceptable base. So we're going to make, again, an alkyl oxonium ion. And the corresponding conjugate base, which in this case is HSO4-. And again, the pKa for that conjugate acid, since it's an alkyl oxonium ion, the same one, should be roughly around -2. So this is still favorable acid-base chemistry. This is why, whether you are talking about doing an SM1 or an E1 reaction, the same first step occurs regardless of what we're doing. The big difference is the conjugate base that is produced in the solution, and that's actually going to be the key to knowing what to do in either situation. But we've got one more step before we get to that point. The next step to talk about is what to do with this alkyl oxonium ion. The oxygen actually has a real problem. If you know from general chemistry, and oxygen's a very electronegative element. And so this atom really wants to have electrons near it, which means it wants to be neutral or negative. And as you can see right now, that oxygen has a full-blown positive charge. So it's very unhappy. It's sharing too many of its electrons with other atoms. So that means somebody's got to go. And as you look at the bonds that you're talking about oxygen-hydrogen bonds or oxygen-carbon bonds. And the more polar bond is actually the oxygen-hydrogen bond. And if that bond were to break, you'd go back where you came from in both cases. And that's actually very favorable for the oxygen. But by doing that, we make a stronger acid. So you can play ping pong all you want, trying to take the proton back off. But it's not going to get you anywhere productive to take that proton off. So if you can't productively get the proton off, you're going to go for the other bond that you have available to you, which is this carbon-oxygen bond. And we are going to break the bond. So this is going to be the same step for both reactions, regardless of the acid that you used. Oxygen does not like having a formal charge of +1. And so you're going to break that carbon-oxygen bond to make oxygen happy. This is going to make carbon very unhappy. And again, you probably remember from class that you can only form a carbocation if you are dealing with a tertiary or a secondary carbon. If it's primary, the carbon says, you can't leave me, and I'm not going to let this happen. I can't form a stable enough carbocation to hang on. So you'll have to watch some of the other videos about carbocation stability, but the main thing here is you are producing a carbocation as water leaves. And it's not happy. It is electron deficient to a great extent. And so we've got to do something to satisfy this carbocation. Now, there are a couple of options for it, and if you come back to our definitions, acids are proton donors. Electrophiles are electron pair acceptors. This carbocation can act as an acid or as an electrophile. It can actually donate a proton that will get rid of its positive charge. Or it can act as an electrophile and accept a pair of electrons. So what it comes down to is what is in solution with this carbocation. Is what's in solution more likely to act as a base and accept the proton? Or is what is in solution more like a nucleophile and more willing to act as a nucleophile and an electron pair donor? So this is actually the key to knowing what we're going to do with this carbocation. So I really want to talk about the properties of good bases and the properties of good nucleophiles at this time before we deal with this carbocation, because I want to make sure you're very aware of what your options are. So good bases, you always want to be a base if you can be a base in organic chemistry. And again, the goal of being the base is to make a weaker acid-base pair, or at least an equivalent acid-base pair. You don't ever want to make a stronger acid-base pair. If what you're doing is going to produce a stronger acid-base pair, you will not be a base. I want to say that again. If what you are going to do produces a stronger acid-base pair, don't do it. If it makes a weaker acid-base pair or an equivalent acid-base pair, that's acceptable. Now, you were going to get really caught up in these definitions. They are usually definitions. They are not always definitions. But typically, in organic chemistry, if something is a base, it will follow three principles. These are typical. If you have to try to decide what something is, this usually works, not always. But a base tends to be negative. It tends to have no resonance, so it's localized. And that localized negative charge tends to be on a small atom. And those typical small atoms are hydrogen, carbon, nitrogen, and oxygen. These are typically what we're going to be looking at. So if I go back to our pKa chart and go to the second of the two pages, you're going to notice several things. Methoxide, hydroxide, ethoxide, the other alcohols. These have localized negative charges on oxygen. That's really important. They have a negative charge. There is no resonance delocalization, and it's on a small atom. Hydroxide was your standard strong base in general chemistry. There are others. Another example of a strong base would be to have a localized negative charge on another element, like carbon. There is a typo on this one, that hydrogen should not be there. Right here, that's a typo in your book. That should just be a carbon. And there are some others that have a localized negative charge on carbon. These are very strong bases. You could also have a localized negative charge on nitrogen. Or you could even have a localized negative charge on hydrogen. Now, some of these others are strong bases as well. They have a localized negative charge on carbon. But there actually is a little bit more to these. You're not going to see them this semester, but these are also going to be strong bases for our purposes. They are negatively charged on carbon. But in general, this is what we're looking for. This is that second half of this table. And that's really important that you realize this. All right. So if something is actually more likely to be our nucleophile and not the base, first thing, it's going to be a nucleophile, because if it isn't, you're going to make a stronger acid-base pair. We don't want to do that. We want to be a nucleophile to avoid that stronger acid-base pair situation. So nucleophiles sometimes have a negative charge. And sometimes they're neutral. Sometimes, if it has a negative charge, it's localized. Other times, it is delocalized. Let me try that again. In other words, may or may not have resonance. And if it has this negative charge, and if it's localized, it will be on a large atom. So we're going to go back to our Pka chart. And these are actually going to be more on this first page here. So those that don't have charge are much more likely to actually be a nucleophile than they are a base. I'm not saying they are never bases. I'm saying they are more likely to be nucleophiles. Now, if it does have a negative charge, it may or may not be localized. So if it's a delocalized negative charge over several atoms, it usually doesn't want to be either, but if it has to choose, it chooses typically to be a nucleophile before it actually acts as a base. Now, if it does have a negative charge, and it's a localized negative charge, it'll be on a big atom like iodide, bromide, chloride, sulfur. There are a few that aren't circled on here that are still preferentially nucleophiles, but these are usually the things we're looking for. Big thing here is a nucleophile tends to be a weak base, because if you picked up the proton, it's going to make a stronger acid. That's what its conjugate acid typically is a stronger acid. And we don't want to make a stronger acid in solution. But if something tends to be a base, it's because its conjugate acid is a weak acid. That's why it's picking up the proton. It wants to make a weaker acid-base pair, and if it picks up the proton, you're going to produce a weak acid. And that's the whole goal of chemistry, is to make a solution that is more stable. So what I've told you is in general true, but the overall truth that will always be true is if you can make a weaker acid-base pair, be a base. If you can't, be a nucleophile. And if you can get that straight, you can do OChem. It will no longer be a difficult thing for you to do at all. And that's what we want. Okay, so going back to our example, I'm actually going to draw out the hydrogens at this point. We have our carbocation. And there are different situations for this carbocation depending on what you started with. Regardless, you got here. So in one situation, you have bromide in solution, and you've already kicked out water, so water is also present. These are your options in the solution to satisfy this carbocation. You have no other options. So out of the two, you need to decide which one is more likely to be reactive at this point. And honestly, they are both conjugate bases of very strong acids. Now, out of these two, the one that is a better nucleophile is bromide because, number one, it has a negative charge. That means it's got more business in solution than the water. Water's neutral. There's a negative charge on the bromide. Number two, it's a localized negative charge. And number three, it's a localized negative charge on a big atom. That prefers to be a nucleophile. It does not want to pick up a proton. If it picked up a proton, you're going to make HBr, a strong acid in solution. We don't want to make a strong acid in solution. That won't get us anywhere. And if we add water back to the carbocation, it doesn't want a proton either. It's neutral. It doesn't have a negative charge, therefore it's already falling in that nucleophile category. These are both potentially nucleophiles. And so if we actually use either of these as an electron pair donor to the carbocation, with water, you're going to go back to the alkyl oxonium ion. That's non-productive chemistry. You're going to go right back up here to the alkyl oxonium ion and reverse this step here. That's not productive. Don't want to do that. And so bromide is really what our options are. And bromide will act as a nucleophile and act as an electron pair donor to this carbocation. And that's why it has the potential to do SN1 chemistry in the presence of HBr. This is why it does this SN1 reaction. Now, if your situation were different, because it can be, we used a different method to get to this carbocation by using sulfuric acid in water. This hydrogen sulfate anion actually has resonance delocalization of this negative charge over 3 oxygen atoms. All of these oxygen atoms bear a partial 1/3 negative charge. It is not localized on a single atom. Therefore, this anion is not a strong base. It's a very weak base. And its conjugate acid is sulfuric acid. It doesn't want a proton. Your other option in here is water. And again, water doesn't want to be a base either. If it picks up a proton, it's not going to produce a weaker acid-base pair. Now, you've got two situations here. The reason they use this HSO4 is because of this hydrogen sulfate anion. It's a terrible base. And it's not that great of a nucleophile either. Does that to say it will never add as a nucleophile? No, it can, and it's actually more likely to do that than pick up a proton, but it's a big guy. It usually just sits there in solution at this point as a specter. It says, I'm not going to help you. And that's why we use it compared to bromide. Bromide's willing to get down to business and help as a nucleophile. The HSO4- doesn't really want to do either. It just sits there, and so it's up to water to do something. Now, water is more likely to be a nucleophile, absolutely, but if water acts as our nucleophile, you're going to go right back where you came from, and this happens a lot. It goes back and forth and back and forth and back and forth because water is potentially a better nucleophile than it is a base. It likes to be this, but it gets us nowhere. And so after a while of playing ping pong, eventually water will do something else. It can actually act as a base. This is why I tell you you can be either or. Water being a nucleophile is non-productive. It happens most of the time, but it's non-productive. So to do something productive, we're going to take a proton from a carbon adjacent to the carbocation. As this occurs, this carbon-hydrogen bond is going to break. Carbon is more electronegative, and carbon takes this pair of electrons to form the double bond. And as a result of that, we're able to make an alkene, which is the goal when we use these oxy acids. And overall, you still have a balanced solution charge-wise because you have HSO4- in solution with H3O+. It's still neutral. You've still gotten rid of water. But this is the only other option that's really even a viable option for a reaction like this.